Hello, everybody. My name is Adam Herrmann, and I'm here to present a paper today that was submitted to the AAS Rocky Mountain Guidance, Navigation, and Controls Conference. The title is Reinforcement Learning for the Multi-Satellite Earth Observing Scheduling Problem. I'd like to thank my co-authors, Dr. Hans-Peter Schaub, my advisor, and Joao Carneiro, who did a lot of the multi-satellite simulation architecture for this work. I'd also like to say that this work is supported by the NASA Space Technology Graduate Research Opportunity. So thank you NASA for sponsoring this work. Okay, so a quick overview. I'm going to go into the motivation for this problem and then give a formal problem statement. And then I'll discuss the methods that we use. So I'll discuss the single agent Markov decision process formulation, the single agent training pipeline, and then the multi-satellite environment deployment. And then I'll talk about some preliminary results that we have and the conclusion. Motivation. So reinforcement learning has shown a lot of promise for the Earth observing satellite scheduling problem for the single spacecraft case. It's capable of generating near optimal planning solutions. It generates a neural network representation of the policy, which can be used to rapidly compute the next action the spacecraft should take. And then you can also take advantage of the action observation action feedback loop. So the agents are responsive to the environment and planning is executed in a closed loop manner as opposed to an open loop manner. However, the prior work, especially work done in our lab, has not explored the scalability of reinforcement learning methods to satellite constellations or scenarios in which you have multiple agents operating. There are several challenges associated with doing this. So first and foremost is the problem complexity. Your action space is exponential in the number of agents that you have. Along with that goes an increase in training time, so that can be considerable. And then coordination between trained agents is a non-trivial problem to be solved. How do you coordinate agents to maximize global reward? So this work really focuses on scaling these methods to a multi-satellite scenario in a simple way. A quick kind of primer on multi-agent reinforcement learning. So there are a number of ways in which the problem can be formulated. First, and probably the most general, is to formulate it as a decentralized, partially observable MDP. And this can handle sparse communication, partial observability, and all of the spacecraft coordinate together to achieve the globally optimal reward. The only problem is that it's very computationally expensive to solve. And like I said before, the action space is exponential in the number of agents. So if you have just 3 spacecraft and 4 actions, the problem is nearing intractability for our methods. You could formulate the problem as a multi-agent Markov decision process. So just assume full observability and free communication. So here the spacecraft do coordinate to achieve the globally optimal reward, but there are some assumptions that come along with it, and still your action space is exponential in the number of agents. The last option, and the one that we use, is to train a single agent MDP, and then take that agent and deploy it in a multi-agent environment where each spacecraft has its own independent decision-making agent trying to image and downlink targets. So there's no increase to training time here. There's no increase to the problem complexity. And another really great thing is that it can scale to any number of spacecraft. Can also be used to provide a performance baseline if you'd like to compare it to items 1 and 2. However, it's inherently not going to be globally optimal because there's no coordination between spacecraft. And it also assumes free communication. Okay, onto the problem statement. So we formulate a multi-satellite EOS scheduling problem where the goal is to maximize the weighted sum of targets collected and downlinked while avoiding resource constraint violations. We have a global target set that's distributed to each spacecraft based on its orbit and access to the targets. And then we also use the Walker Delta constellation notation, where you have T spacecraft all on the same inclination distributed amongst P orbital planes. And then you can also define some relative phasing between adjacent orbital planes. We assume instantaneous cross-link communication every 6 minutes or every step through the environment. And there are 7 ground stations that the agents can downlink their data to. A quick note on the target notation. So I mentioned there's a global set of targets that are distributed to each spacecraft. So each spacecraft can have anywhere from 50 to maybe 1,000 targets available for imaging. But there's no way that it can possibly image all of those over the planning horizon. And furthermore, there's no reason that it should consider imaging all of those at every time step. You might not see one target for several orbits, so why consider it now? So what we do is we formulate a subset of targets known as U, and that just contains the next however many, the next J upcoming targets available to the spacecraft. And we take this subset of targets, and this is what we use in the action space, which I'll describe shortly. So onto the single agent Markov decision process that we have defined. So a quick primer on Markov decision processes. So they're defined by the 5-tuple, which is the state space, the action space, the transition function, and the reward function. There's also a discount factor. And the agent selects an action A in state S using some policy to maximize the sum of all future reward. And that's depicted here in this diagram where you start in state, the agent starts in state S naught, takes some action A naught, transitions to a new state, and then receives a reward. And then this process continues until either infinity or early termination of planning or the end of your planning horizon. So onto our specific formulation of the problem. So the state space includes spacecraft position and velocity states. We also have a number of states that deal with the spacecraft resources, so like the battery level or the level of the data buffer. We have an eclipse indicator, which helps the agent make decisions for maintaining its battery levels. And then we have different ground station states for downlinking and also ground target states for imaging. In the action space, the first 3 really deal with managing these spacecraft resources. So you have charge, downlink, and DSAT. And then the rest of the modes are imaging modes. So the agent can image target 1 in U or target J in U, and there's an action for each target included in there. The reward function is formulated as a piecewise reward function. So the agent receives -10 if it fails to manage any of its resources. If the agent enters the downlink mode, we loop through all of the targets available to it and check, was the target downlinked for the first time? And if so, 1 over the target priority is returned. If an imaging mode is entered into, we look at that target and we say, well, is this the first time that it's been imaged before? If so, a small reward bonus is applied. And otherwise, we just return 0 reward. Now onto the single agent training pipeline. So solving for the policy of a Markov decision process is really solving to maximize the sum of all future reward. And one way of looking at this is through the state action value function, Q. So this basically just represents the value of a particular state and action pair. And it's the expected value following some policy pi of the sum of all future reward. And then here in this example is just the finite horizon case. If we solve for the state action value function under some policy, we can generate a new policy, pi, that's simply the argmax of the state action value function. So what is that policy that we're solving for? Well, we use Monte Carlo tree search to generate lots and lots of training data. And then we use artificial neural networks to regress over the state action value function computed from Monte Carlo tree search to come up with a neural network representation of it, Q sub theta. So in the diagram below, you can see we generate data, so thousands of data points, regress over them with various ANN architectures, and then validate each of these ANN designs in the single spacecraft environment. So for training generation, we use Monte Carlo tree search, which is an online search algorithm that runs a number of simulations of the environment at every step through it to build an estimate of Q and select the best action. It follows this selection, expansion, rollout, and backup process. And it works quite well. We've used it in the past for a couple other problems, simpler than this, but it's quite stable, and you do get really good estimates of Q out of it. So we take those estimates of Q and we regress over them with a variety of neural network designs. So we do like a big parameter search. In the bottom left table, you can see really the two things that we're sweeping over are the number of nodes per hidden layer and the number of hidden layers. So we're basically just trying to size our neural networks. Some of the other parameters in that table we've looked at in past work, but it's not covered here because we've pretty much nailed down what works and what doesn't. So on the top right plot, you can see we look at the performance of the trained agents when the networks are sized at 50 nodes per layer and anywhere from 3 to 9 hidden layers. And then on the bottom, we repeat the experiment, but for 100 nodes per layer. These box and whisker plots are really nice because you can get a good sense of what the distribution of reward is. You can see if there are any failures, and it enables you to basically pick the agents that perform the best in training for deployment. Here are a couple validation results. So for each size of view, or for each number of actions, number of targets we include in the action space, we select the best neural nets that we've trained, and we deploy those in the environment, and we benchmark for reward and the mean number of downlink targets. And you can see that when we include more targets in the action space, the agent can make more trade-offs between targets, which is exactly the desired behavior. So we take these trained agents now and we execute them in a multi-satellite environment, which I'm going to talk about next. So the diagram on the right gives a kind of an indication of what this looks like. So we use the Basilisk Astrodynamics software framework to create a multi-sat simulation. And then we wrap that multi-sat simulation in a gym environment, which provides a standard interface for decision-making agents to interact with it. You can see that in the simulation framework itself, we have one environment class that holds all of the gravity bodies, eclipse models, ground stations, ground targets. And then each spacecraft has its own dynamics and flight software class. So the dynamics class has anything spacecraft related, like the batteries, panels, imagers, the attitude control system, the physical elements of it. And then the flight software class has everything for controlling the imager, the attitude control system, etc. The nice thing about using this architecture is that we can set it up and set the initial conditions with just a single line of code. It's very fast to do. And then as we're stepping through the environment, basically we just loop through the observations from each spacecraft, run those observations through the same neural network architecture we used for the single agent case, and then just collect a list of actions, which is then passed to the environment, which then executes all those actions. One thing to note before I get into the results is that we don't duplicate reward. So if one spacecraft images and or downlinks a target and another spacecraft does the same, well, reward for that target is only returned once. Okay, now on to the results. So for this first experiment, we vary the number of spacecraft and target numbers, and we plot the mean global reward, or the total reward achieved. So we do this for different numbers of spacecraft, all the way from 5 to 30, and we hold the number of orbital planes constant at 5, so we're not changing too many things at once. And you can see that as you add more spacecraft to the simulation, your mean global reward increases, as you would expect. And furthermore, as you add more targets to the simulation, mean global reward increases up until a certain point at which the spacecraft can't really collect any more targets because, well, they're basically hitting their resource constraint limits, like the data buffer size and how frequent the downlink windows are. We also repeat this experiment for just one target in the action space and then 4 targets in the action space. We also looked at this same experiment, these same results, but from the perspective of mean local reward. So take the mean global reward, divide it by the number of spacecraft. And what you can see is what we would expect. As you add more spacecraft to the simulation, there's more competition between the trained agents. So reward per spacecraft decreases. Another interesting thing to note here is that the reward per spacecraft for one target in the action space is far worse than 4 targets in the action space. We're not entirely sure why that is right now. It's likely to do with poor function approximation, and at least partially to do with what I'm about to show you on the next slide. So one thing that we noticed was that if you look at this plot here, for 3,000 actions and let's say 5 spacecraft, the reward per spacecraft reaches about 16, which is much lower than what we saw during training. We got up to, I don't know, 26, 27. So this is almost, not quite 50%, but it's not looking good. And this was quite perplexing, and we wanted to look at why. So what we did was we plotted the mean local reward, so reward per spacecraft, versus the longitude of ascending node of each spacecraft. And we found that there was quite a large dependency there. And the reason is because of the distribution we used for the initial conditions and training. You can see our longitude of ascending node was sampled between 0 and 20 degrees. So the agents perform just fine between 0 and 20 degrees, but the further away from that you get, the lower the reward becomes. And then as you begin to approach 360 degrees, the reward increases again. So this should be corrected in future work simply by just widening the training distributions. But it is interesting to show that, we kind of degrade gracefully almost, and then start to go back up. But there certainly is a dependency on your training conditions. So that's something that needs to be corrected. So in conclusion, we've shown here that agents can be trained in a single satellite environment and successfully deployed in a multi-agent scenario. As I showed on the last slide, there's a reward dependency on the distribution of training data. And for future work, we're going to explore cases where there's no communication between spacecraft, line of sight communication only between spacecraft. And then we're also going to benchmark performance where you have coordination between spacecraft. And by coordination, I mean they're trying to maximize global reward. So that's really as simple as taking Monte Carlo tree search and applying that to an MDP in which every combination of actions is considered for all 3 or 4 agents. Unfortunately, it's going to be very computationally complex. So we're probably only going to get to look at it for the 3 or 4 spacecraft case, but it will give us a good indication of what that performance gap looks like and whether or not future work should explore ways to reduce the problem complexity while also handling global coordination. So a quick slide on references, and that's the end of my presentation. So thank you for watching.